Okay, good evening. Can you hear me?
Good evening, sir.
Doing, sir.
Yeah, yes, okay. So, what are we going to discuss today? What do we need to discuss? Shall we just quickly go over the week 5 and 6, whatever is there, main very important concepts alone?
Yes, sir.
Yes,
So, just what is most essential, there are like too many things there. So, I am not going to go over all of them. Maybe we can just go look at uh, just the elementary things which we need to look at. Okay. So someday these notes will get updated, but for now there are optimizers and regularizers. Okay, so those are the 2 weeks. Then week 7 you have some more things on initialization, not normalization, and then different activation functions and all that. Okay, so let me first hide the.
So,
Okay,
where can I find these notes, sir?
notes I will upload. So currently it's empty. Empty in the sense I have only added the key equations like updates, and these are all empty. So for example, there's nothing okay, bias variance something is there, but rest are all empty. So I'll have to work on them a bit. Mm,
Okay, sir. Okay.
okay, so yeah, see, in terms of optimize, I'll just talk from the quiz point of view today, right? I won't be not just quiz point of view, but in general from practical standpoint, right? What you really need to know if the course is titled Introduction to Deep Learning, what should you know? Okay, if the course is titled Comprehensive Course on Deep Learning, then it's a different issue, right? Then you have to study all that is there in every single minute of the lecture. You'll have to know. But if it's a good foundations that you need to have, then what I'm going to tell you today is what you need to focus on. Okay, so we have to start from week 4 itself because that's the base for all the optimizers, right? So what all optimizers should you absolutely know? These are the optimizers, right? So you need to know gradient descent, of course, basic, right? And then you need to know the stochastic version of it. And then, so when I say stochastic gradient descent, I also include mini batch gradient descent with varying batch sizes, right? If batch size is 1, that is typically called SGD. But any stochasticity, I'm just calling it SGD. And then momentum gradient descent, Nesterov accelerated gradient descent, ADA grad. So these first 4 are not adaptive in nature, right? So they don't adapt to the learning rates. So they don't have adaptive learning rates, right? So first 4 is one set of optimizers, and then you have AdaGrad, RMS prop, and Adam. Okay, so these three are have some notion of adaptive learning rates, right? So depending on which direction you are looking at, the weight updates are different, or the learning rate used in the weight update is different. Okay, of course, if you look at the lectures, there is this NADM, there is Max, some different Max prop. There are like I think 3 4 other optimizers. ADA deltas there. So from if you look at textbooks, right? If you look at Bishop, for example, Foundations of Deep Learning, which got released last year. Okay, that only covers GD, SGD, Momentum GD, NAG also I think it covers, and then it covers ADA-grad, RMS prop, Adam. It stops there. It doesn't cover NADM and the Max prop and all that. Okay, so those are all. Once you understand these 7 optimizers, you kind of know what the others are. Okay, in fact, Adam itself is it's a mix up of mashup of RMS prop and momentum. If you think about it, so you need to focus on these 7. Okay, both from exam point of view and from a practice perspective, right? If you are going to go out and implement, mostly by default you will be using Adam. Okay, sometimes you'll also use SGD itself, right? More batch gradient descent itself you might use mini batch gradient descent. But beyond Adam and SGD, unless your your problem is so hard to train using these two, and you have to come up with something very novel. You generally won't go all that, right? So Adam works pretty good in most of the real world problems that you are likely to come up with against. Okay. Same with regularization, right? So regularization is kind of slightly easier. If you look at week 6, it's all really MLT. Whatever you have done in MLT, regularization is just the trade-off between uh, model, how big a model you have to choose, making sure that you don't overfit on the training data, and you generalize. So goal is generalization. So generalization means what? Performing well on the test data. Okay. So the theoretical way to understand that is using bias variance trade-off, and there is a very important curve that I will show you. It was there in the lectures also. So, and then it's all familiar stuff. L2 regularization we have already seen in MLT in the regression week. Okay, just add lambda times the norm squared of the parameters. Early stopping also is very intuitive. All the rest, at least till here, there is some proper mathematical backing. But from here, even though we have shown some, there's a lot of math in the lectures if you see, but all of these are really very heuristic approaches, right? So you can argue that if you stop early, that this happens, Hessian and all that. I hope you have seen there's a long derivation, right? So all that is good, but essentially these are more practical sounding things. Okay, you can intuitively understand why early stopping makes sense. You just need to look at the loss curve, the training loss, validation loss, and you will realize that stopping early is a good thing to do. Same with data augmentation, right? You are giving more data to your network. Parameter sharing, you will really be able to appreciate only after week 8. Tying probably only after last 2 weeks. What where tying gets used. Noise at the input, again very simple. So simple technique to introduce some more, to make things slightly harder for the network to learn. In that process, it will generalize method. So the only novel thing, so these are all common. Okay, these are all common to all machine learning models. Okay, the only thing which is kind of novel for a new from a neural network standpoint is dropout. Okay, ensemble methods have been there. So we already studied bagging, boosting. You can bag random forests, bag decision trees that will give you random forests, right? So it is pre-deep learning, that it has got nothing to do specifically with deep learning. Same with all these things, right? Perhaps parameter sharing and tying also is slightly specific to neural networks, but all the others are things you have already seen. Okay, so this is what 5 and 6 weeks, 5 and 6 are containing. Okay, this is the content. So let's look at the first optimizer. You already know all this. So this is, what is this? Can someone tell me what is this equation represent?
Loss function.
Correct, loss function. But how did we get this L of WT plus W minus WT transpose gradient of loss respect to WT?
So we initialize that loss function.
Uh,
Is that back propagation thing?
Sorry,
In the back propagation that we learned.
back propagation. But really, if you look at it, this is nothing but Taylor series, right? So this is, so remember. So see, this is very important, right? So Taylor series approximation for the loss function L around the point, around which point?
Omega t.
Yeah, right. So yeah, I call it WT, but it's fine. Yeah, it could just look like omega. So doesn't matter, right? So both are, you can, both are fine, right? For the sake of this lecture or this session, we'll call it WT, right? So the loss is a function of weights, and what is this W? Is it a vector? Is it a scalar? Is it a, it's a vector, right? So it's a vector of weights, and if you plug in WT, what will happen? This will be 0, right? So this part this part will be 0. So it's just L of WT. That's one way to check if your approximation is correct. And if you slightly perturb W around WT, then this is how the loss function's value will look like. Okay, so this is what approximation? This is a Taylor series approximation, but is there anything specific that you can say about this? It is what order approximation? Yeah, it's a linear approximation.
Linear.
Yeah, first order approximation or linear approximation. Okay, if you want to be more specific, you can also go ahead. And what will you add here? If you want to add one more term to make this approximation.
Base.
What is it? Sorry, I didn't get it.
Base.
You will add the
Set the-
Hessian, right? H.
So we will add a second order.
Correct, right?
Thing. Yes.
The second order term. So you'll do so W minus WT transpose Hessian times W. So something transpose HW, right? So this is your quadratic form as you have studied in MLF. Before you will have a 0.5. Okay, so but then we don't want this. We will never go into second order optimization techniques in this course. We will stop short at first order techniques. Okay, so this equation, never forget this, because this is where gradient descent comes from, right? So if you want to now decrease the loss, decreasing the loss means what? L of W should be smaller than L of WT. Okay, so L of W. So what do we want? We want L of W minus L of WT to be positive or negative. So when I say W, I mean W new point, WT plus 1.
So negative.
You want this to be negative, right? Which means this is a dot product, right? So this dot product also has to be negative, right? So this is nothing but the dot product, W minus WT transpose. This is gradient of L with respect to WT. So this is where we get the idea that this is WT plus 1. Okay, we have to move in the opposite direction of the gradient. That's what it means for the dot product to be negative and in the maximum possible way, right? That will happen when they are anti-parallel. So this quantity should be negative of the gradient. So isn't this enough? Why do we add this eta? What is the point of adding an eta there? This itself will work, right? What is wrong with this equation?
Sir, this equation won't learn anything.
Okay, why will it not learn?
So because this is fixed, or it will pass on. If it's not there, it might shoot off the minima.
This shooting off, that's the problem, right? So see, this important point is Taylor series. When you say Taylor series approximation, this holds good only around a very small range. Okay, you can't. It's like you're at WT now. You can't step too far away from WT. If you do that, this approximation is no longer valid. Therefore, we typically only move by a very small distance in the opposite direction of the gradient. Okay, that's why this learning rate matters. Okay, so please remember these things. This is the basic principle of gradient descent, right? So now you can notice that WT plus 1 is WT minus eta. This is your usual update route. You must be familiar with this by now. Okay, so there's another point hiding here. I'm calling this point when W naught is initialized appropriately. So why do you think this is important? Can you initialize the weights of the network with all zeros, for example?
Yes, sir.
Okay, so this is an important point, right? You have to think about this. Okay, so initializing all the weights to the same value is a dangerous thing to do in neural networks. Do you see why that could happen? Why that is the case? So the claim I'm making is, this is the claim I'm making. So all the weights of a network should not be initialized to, let's say, 0 to begin with.
So the gradient will be 0.
Okay, then I will change this to should not be initialized to the same constant. So it could be 0 or non-zero.
Sir, because then we are giving the same importance to everything.
Yeah, that's correct, right? So if you do this, all the neurons become identical. You see why that is the case? See, do you agree? Do you agree that every neuron, let's say one hidden layer, first hidden layer. So what will be the first hidden layer neuron? It'll take input from all input neurons, right? And what will it compute? It will be W1 x1 plus Wn xn, correct? This is what the first hidden layer neuron will do. Now, in that same hidden layer, another, let's take second neuron. Let's call it W prime, W1 prime. Okay, that is also going to take all x1 to xn as input. That's not any different. Okay, remember all neurons take all the input from all neurons in the previous layer. Okay, now if I set W1 equal to W1 prime and W2 equal to W2 prime, so on, then do you see that these two neurons compute the same value no matter what the input is?
Yes, sir.
Okay, so which is why, and this is forward pass, but if you extend the argument, in the backward pass also, the gradient updates will be the same. If the values are set as same constant, both in forward and backward pass, W1 and W2, W1 prime, W2 prime, all of them will be identical. So this problem is called symmetry. There is a symmetry, right? So you have to break the symmetry. Okay, you have to do what is called symmetry breaking. And how do you break the symmetry? By
Initializing to different values.
initializing weights with random values, right? Typically, there are several ways of doing this. One of the common initializations is to choose 0, normally distributed values, some 0, epsilon square, right? So small value of epsilon. You could also use uniform, so uniform distribution with minus epsilon to epsilon. Okay, both are valid ways of initializing. The main point is you have to break the symmetry so that different neurons end up learning different things. Okay, so that is, I'll include this later on in my notes. For now, or maybe I'll let it stay here. So this is what the initialized appropriately means. Okay, so that is gradient descent, nothing fancy there. So motivation we now know, right? So you small approximation around that initial starting point, and then you move in the negative direction of the gradient so that the loss function decreases by the maximum possible amount. You take small steps in this direction, that is given by the learning rate. You can't take very large steps, that will make your algorithm diverge, right? It will not learn anything. And you have to initialize the weights appropriately. Okay, so that is gradient descent. Why do we need the stochastic version of it? Why not just use vanilla gradient descent? What is the problem with using that? What will
So
go
data
wrong?
size is data size.
Correct. Yeah. So the computational constraints, right? So this is the total loss when you compute it on the entire training data set, n data points. Computing the gradient on such a huge, so typical, you might have 1 million training examples, right? So imagine 1 million training examples and having to compute the gradient on of a equally big neural network with so many, say, 20, 30 million parameters. That's going to be a very computationally intensive task. So you can't do vanilla GD, right? Even though that would be an optimal thing to do, you can't do that practically. So you have to do it in small batches. So you can efficiently compute the loss and the gradients for a small batch size Okay, B, capital B. Capital V is typically chosen to be some power of 2. So 32, 256, 128. Okay. For certain hardware reasons, sometimes or often capital B, the batch size is a power of 2. Okay. And then you take updates. So the update rule remains the same. Okay. So what all things you need to remember here? I actually made a list of points here, but you already done quiz 1. So I think you know all that, right? So if the batch size is B, then you will, how many updates will you make if there are n data points in one epoch? N by
And B.
n by B updates, you will do all that, right? There was a question also in the quiz. Uh, so one point that you have to notice, you have to shuffle the data set. This is a practice related issue, right? So when you actually implement gradient, stochastic gradient descent or mini batch gradient descent to be specific, you have to make sure that you shuffle the data set before you pass the batches to your learning algorithm. Okay. If you don't shuffle the data set, so I hope you understand what I mean by shuffle, right? Mainly the class label should be shuffled. So you should not pass, if your batch size is 32, let's say, you should not pass all 32 examples which are from class 0 in one batch. Why is that a bad idea? Why can't we pass multiple batches in sequence where all of them belong to the same class?
Will it be biased? Will the model be biased towards
Correct.
particular class?
Yeah, you're right. Right. So in a sense, the model will be biased towards that particular class. See, this is a very important point. Here, what is this? What is this grad t actually? This is the gradient of the loss function actual notation, right? With respect to what?
The weights.
The weights,
Okay.
right?
Weights.
But is this the full loss function? Is
It's
this
the
L
either
or
the
is
stochastic or the mini batch loss.
Approximation of the loss
correct, right?
function.
So it's across the mini batch. So what is happening is if LB contains only data points from one class, it's as good as training in some sense a single classification problem, right? You are only training the network to minimize or reduce the loss of one class. That doesn't guarantee that it will perform well on all the other classes, right? So this is, but it is particularly bad if you have a mini batch having only one class. Okay, so typically what is done in practice is every epoch, at the beginning of every epoch, the data set is shuffled, and then you randomly sample once you shuffle, you can just sequentially go, right? First 32 data points, then next 32, next 32, and so on. So that's one point you have to remember when you're doing mini batch gradient descent.
So one small thing.
Yeah.
In MLP, we came across that sampling thing, stratified sampling. So what that has to do with this one? Do we deal something related to this in that also, that stratified sampling?
I'm not sure if we do stratified sampling here. It is more of just a random sample. The if the data set is imbalanced, for instance, then yeah, then that might cause an issue. But that is more of that's something you'll have to probably deal with even before you begin passing data to the learning algorithm, right? So
Okay.
yeah, I'm not very sure about that. How stratification will work here.
Okay. But in both, we are about to achieve the same goal.
Sorry, how to achieve?
In both, we are achieving the same goal. Na? We are trying to achieve the same goal.
So stratification is that what we are trying to see what we are trying to do is we are trying to approximate L using LB. That's our goal. So we want a loss. So we want a batch that is the term I would use is representative of the total loss. Okay, which so L this LB should be representative of the total loss L. That's what we are trying to achieve, right? So in which case, if there are all data points belonging to one class, that's an issue because it's not representative of L. But the stratification, I'm not too sure whether we. Yeah, to my knowledge, I think it has to be fixed even before you start passing in batches to your algorithm.
Mm. Okay. Okay.
Okay, maybe we can check this up later. I also don't know.
Okay.
Okay, so what else is important in SGD? I don't think anything else is needed. So yeah, we can move on to momentum. So this momentum, there are actually different motivations. If you look at historically, if you look at it, even if you study textbooks, they have motivated it slightly differently. So this is from Bishop's textbook. So this is the center of the valley is the minimum, and what happens is you start from here, and if you think about it, gradient descent is going to oscillate in this region. Okay, this region is called a valley. So if you, I hope you can visualize this. This is like a the slope changes very rapidly in the vertical direction. We call this direction across the valley, and this horizontal direction u1, right, is along the valley. So along the valley, the slope is gentle, uh, or rather, it changes very gently. Across the valley, it changes rapidly. So if you actually train gradient descent starting from this point, it is going to rapidly oscillate across the valley because, as you can imagine, the gradient value will be very high in the vertical direction. So there are going to be a lot of oscillations perpendicular or along U2, which is going to hinder the speed with which gradient descent converges to the minimum. Okay, so this is the initial motivation for coming up with momentum based GD. If you look at our lectures, there is a different motivation where we, of course, we want to speed up learning. And that's the motivation, right? If you remember, we want to speed up learning in gentle loss surface, and hence we use momentum, and that introduces oscillation. Is what the lecture we have mentioned in the lecture. This is slightly different take where even in gradient descent there are oscillations. Okay, it's not that after you introduce momentum only then there are oscillations. No, right? So you could be in a situation where there are oscillations even with gradient descent, and momentum kind of helps in dampening these oscillations. Okay, so I encourage you all to go back and look at these textbooks for a different perspective. So yeah, now what do we do? This is the update. So you have what is called a momentum parameter, which controls how fast you want to move along the direction that you have been moving along so far, right? So this UT is some kind of a history vector. So it keeps track of how fast you have been moving, and this is what kind of an average. What is this called? It
Accumulation history.
is a weighted average. Is that right?
Hmm.
So what kind of a weighted average is it? Is it like, are the weights equal for all time steps?
No, like we have taken a scale.
Yeah, they are scaled.
Hmm. Beta.
Scaled in what manner? Are they scaled linearly or exponentially, right? So
Exponential.
they're exponentially weighted average. So you can also think of this as a moving window, right? So I hope you are all familiar with the moving window. Okay, so think about, say, a window. Window will start from some t equal to a window of length phi, right? So you can think of a window of length phi, right? So what would that mean? It means I am only concerned with what happens in the last 5 time steps, right? So I'm only concerned with the behavior of my gradients in the last 5 time steps. So beta will actually control all these things. So I just want you to appreciate this fact. So if beta is say 0.9, what do you think beta power phi is going to be? Zero is this, then what is beta power phi going to be?
It will be very small, and then it
Very
won't
small,
give much
negligible.
weightage to the when it is on the fifth iteration. So automatically the window length will remain 5.
Right, correct. Yes, that's what I wanted to get at. So maybe I should choose a smaller beta. This is for this window length. It's kind of large beta value. So let me say beta is beta is 0.5 for instance. Beta power 5 turns out to be something around 0.03. Okay, so I hope you get the idea, right? So your window, once you choose beta, some kind of a window gets chosen, and what you care about is the gradients in that window. Okay, anything beyond that is really not going to affect your weight update because it's going to be insignificant, right? The beta power t is going to be so small. So there's actually a nice argument which I encourage you to look at, which what happens if all the gradients for a certain number of time steps are the same. You will see that the effective learning rate gets bumped up. Okay, so that's the effect of momentum, especially when you are in regions where the slope is kind of similar. Okay, oh, I have done this here. Okay, so this is what I wanted you to do, but you can take a look at this. So what have I done here? Ut I have unrolled in time, unrolled ut in time. So this is beta ut minus 1 plus wt, right? So this is retained, and then ut minus 1 is beta ut minus 2 plus gradient of wt minus 1, so on. So if you unroll this in time, you will see that you have an expression like this. So if you are in a region where the slopes are kind of similar, okay, you can think about a gentle region where for quite a few time steps the slopes are the same, then you can replace all gradients with just one gradient. Okay, and then you have this kind of a summation, and this is a geometric series, as you know. So if you sum it, you get something like this, right? So what can you say about this quantity? Is this quantity greater than 1, less than 1? Say t equal to 100, for instance.
So less than 1.
So beta is 0.9, t equal to 100, 99, let's say. So what will this become? This will specifically become 1 minus, what do you think beta per 100 is going to be? If beta is 0.9.
It is going to be near to 0.
Yeah, it's going to be a very small number, right? So I can as well ignore it. When compared to 1, beta is going to be a very small number. Beta per 100 is going to be a very small number, right? So now can you tell me what? So this is what this is. I can call it effective learning rate, right? So you see that all places, right? Eta prime into w. So eta prime is it okay? There was this is not eta prime, sorry, but I hope you get it. So when you actually plug in ut here, you will get a eta prime will be eta by what I'm. Do you get what I'm calling by eta as eta prime? Eta by
Eta upon minus beta.
yeah, eta upon 1 minus beta, right? That is what eta prime will be. So will eta prime be bigger than eta or smaller than eta?
The quantity will be greater than 1, so eta prime will be greater than eta.
Correct, right? So the effective learning rate is greater than beta. So I'll delete these steps. So what I'm trying to convey is the effective learning rate is given by this quantity, which is eta prime equal to eta by 1 minus beta. And since beta is fractional quantity, this is point, for instance, this is 0.9. So this will be what? 1 minus 0.9, 0.1. This will be 10 times eta, right? For a particular value of beta I'm saying. So when you are in a region where for a long time, for like considerable amount of time, you are moving in the same direction. Effectively, what does that mean? That means increasing or bumping up your learning rate so that you move really fast. Okay, so the effect of momentum is to bump up the learning rate in regions where you're sort of, that the direction is kind of the same. Okay. So that is one intuition that you must have. And this is what momentum does. So this is after you use momentum. So this one is before momentum. You see that there are these oscillations, but here the oscillations have dampened. Okay. Now they have dampened in the vertical direction. Can you see why vertical direction the oscillations have come down? By looking at this equation, why do you think in the
So
vertical?
because we are this equation is about W, not B.
Okay, correct. Okay. So, okay, can you tell me what happens by looking at this diagram? What happens to W1 and W2? What can you say about gradient of W1 and gradient of W2 in terms of sign along the vertical direction? Or look at this, right? So this is W1, this is W2, W3, W4. What happens to the sign of the gradient in the vertical direction? It keeps flipping, right, between positive and negative. Do you notice that? So when you use momentum, if the momentum is taking you along one direction, say it's taking you along this direction, okay, you wish to move down, but then this this quantity now currently points here. So that's going to dampen, or it's going to lessen the oscillation in the vertical direction. Okay, that's the effect it has on U2 direction. On U1 direction, the effect it has is to speed things up. Okay, so if what I told is not making a lot of sense, you can go back to this textbook by Bishop. You can also look at other textbooks. They all talk about this example only. All right, so that is there for momentum, and then this nag is kind of boring. So this nothing much
Excuse me.
there here.
Sir, if you could
Yeah.
mention that point as a comment, that direction, oscillation in particular direction, that vertical.
Yeah. So yeah, I will mention it. I'll kind of need to polish the argument, but I will mention it. Yeah, I'll keep a note.
I had a question. So, in the lecture, sir, so not in the MGD lecture, but after the Adam and every lectures, so there is another notation of weighted averages used, like beta and 1 minus beta. So, how does the momentum change when we use beta and 1 minus beta instead of what we're using right now? And how is like this preferred over that one? And I could not
These
get
are
that why.
Yeah, so
Like
I
we have.
think it just goes off by a factor of 1 minus beta. So apart from that, it's still the same exponentially weighted average, but for whatever reason that formulation comes in, I don't think there is any. I don't think we can prove that this is better than that. But
But I
that's
mean, if
I
you're
also
taking
don't have
1
a
minus beta, the weight for the gradient goes down significantly, right? So like if beta is 0.9, so earlier we were taking 1 as the weight for the gradient, but
correct.
now it comes down to 0.1. So doesn't that take down the weight of the like the value of the gradient to be added to the history vector too low? And doesn't that change the whole idea of why
Exactly.
momentum is used, because like it's used to speed up the entire process, right?
That's a good point. Yeah. Why do we? So that's not mentioned in the lectures also. It's
I
just
mean,
that.
I was like trying to understand this MGD. There was a question in week 5 about comparing MGD and Adam. So I
Okay.
was like trying. So I found this formula somewhere, like where the weighted average was used as beta and 1 minus beta. And I think Sir also mentioned it somewhere that these are the two common ways of assigning weights. So I just
Hmm.
wanted to know like how significant of a difference is that, and in which cases that type of weight can be used, whether weight assigned to the gradient is 0.1, like 1 minus beta.
Okay. Yeah. Good point. So I also don't. I don't. To be honest, I don't know why when that switch happened, or why one is. Is one better than the other? That is also something I don't have an answer for, but we'll have to dig up and see if there is an explanation somewhere. See, the problem is I also face the same difficulty when trying to understand many aspects of deep learning, not just in the lectures, but even other ways. So, in many cases, there is no clear cut reason why something works, right? So, most of it is empirical. So, even if you look at Adam, so Adam is the most popular optimizer. We still don't understand why Adam works so well, or in fact, there are. If you go back a few years, there was a research paper apparently, or a string of research papers where they compared Adam against SGD, right? Stochastic mini batch gradient descent, and those papers claim that stochastic gradient descent generalizes better than Adam. Okay, and they have argued that it leads to slightly lower loss values, which helps in generalizing better. So, is there a proof that you can give? No, there's no proof, or only heuristic arguments, right? You say that, okay, this could be happening, this might be the reason. That is all we can say at the present moment. But this is a very good question. I don't deny that part. Unfortunately, I also don't have a convincing answer. I also don't know why one is.
Okay. Okay,
But
I'll try to
yeah,
find an answer if I can.
sure. If you find, please let us know in Discord or.
Yes, sure. Sure.
Okay. So please keep asking these questions. See, some of them might become research questions which you are very passionate about and you might find an answer. Okay. In fact, there are people in the deep learning community gave one explanation why this ReLU. How many of you have started learning about learning week? So going through week 8 content. Anyone who has started? Okay. So there is this residual connection which you'll study in week 8. Okay. So where you have a hidden layer, input to the hidden layer, and then there is some operation, outcomes activation. So in a residual network, there is a concept called residual layer where you add the input again to the output of the hidden layer. Okay, it's like seems stupid thing to do, but so what I'm saying is, let's say you have x. Okay, x becomes some what w transpose x plus b. That's what is the pre-activation, right? And then you apply some activation function. So this is your activation. Okay. Now in a residual network, what will happen is residual layer. You do this transformation and then you add the x back to it, and then you go to the next layer. So apparently, adding these residual connections helps the network learn better. So initially, researchers thought this was happening for some specific reason, but later on they changed the reason why this is happening, right? Or rather, they came up with a different explanation. So apparently, what happens is that the adding this residual connections makes the loss surface smoother. So once you make the loss surface smooth, once the loss surface becomes smooth means uh, it's very easy to navigate. Okay, so imagine a mountain which is having a very smooth terrain. Trekking will be easy, right? As opposed to a very rugged terrain where you have to where there are deep pits and valleys and cracks here and there, right? So smoothness helps in better optimization. That is the reason, apparently, right? So for a given phenomenon, this explanation itself ended up changing. So the deep learning is still is that kind of a field where you can't prove things. Unfortunately, you can come up with some kind of heuristic explanations at best. Okay, so we'll try our best to understand whatever we can. This nag is there, right? This look before you leap. You already know that you're going to go to this UT. Is this correct, by the way? Yeah. So you make that update first, and then compute the gradient, and move by eta times ut, right? So that is there. Okay. So this is week 4. Now we come to adaptive learning algorithms, where the learning rate is adapted based on the direction of update. Okay, so which direction in the weight space you are going to update? Are you going to update W1 or are you going to update W2, so on and so forth, right? Now, what do you keep track of here? You keep track of the values or the magnitudes of the gradients, right? So you have to understand this part. So what is gradient of, what is this quantity? This nabla of Wt squared. This is actually the following thing, right? It is, let's say Wt has only two components, then this will be what? This will be dl or del L by del W1, comma, del L by del W2 square, right? So this, or I should maybe enclose this within brackets. Okay, this is, I hope you get this. This is an element-wise multiplication. This is what it means. Or I can just change this to, there are like capital D components in this vector. This, you can add a dot 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 and one comma, right? So there are, this is an element-wise product. I hope everyone is clear with that part. Okay, that's what this means. And this also means what? Element-wise multiplication. So this would, if you only look at this quantity and look at, say, the ith component, it would be what? It would be eta by square root of dou L by del L by del Wi. This whole thing is squared plus epsilon into, what would this be? Del L by, okay, that is one component in the, or rather this will be Wi current value minus. Do you get this part? Is everyone clear with this? What the computation looks like here, element wise? Okay, any question, confusion there?
So that corresponding value to Vt in the denominator.
Sorry?
In the denominator, in the under root, that square thing.
Oh, sorry, this is, yeah, this would be, to be more specific, this is Vt minus 1, that component of Vt minus 1 plus this. Yeah, this should be just, you are right. That's why I asked. I made some mistake. Yeah, this is Vt minus 1, the ith component. It gets very nasty, but I hope you are fine with this part. Mainly I wanted to stress is this is element wise. Okay, so as long as you understand that, fine. So what is the issue with this update? Why is this? First of all, how is it different from gradient descent and its cousins?
The effective
It is adapt.
learning rate is changing, adapting.
Okay,
I think the difference is, of course, it is utilizing the history, but in gradient descent, we were utilizing the history with the in updating the gradient. Like we are utilizing the history in only learning rate, but in gradient descent, we were utilizing that history in boosting the gradient value. That
okay, all right. Okay, so yeah, your effective learning rate is now going to depend on which direction you are looking at, right? So which component. So if you're looking at some component which is having very small, very gentle slope for quite some time, then that is going to have a much higher learning rate compared to a region where the slope is larger. Okay, so effective learning rate, right? So this, you should understand it relatively, not absolute, not in absolute terms, but relative to steep loss surface. A gentle loss surface is going to have a higher learning rate. Okay, effectively. So that's what is happening. So this is that's the adaptive nature of it, right? It adapts to where you are in your loss space and what the gradients are or what the partial derivatives are in the different directions. Okay, so one issue, yeah. Now let's look at one minor change, and I'll ask you what happened. So can I remove the square from this?
Then that would be a problem because direction comes into picture and the way so the gradients may cross out themselves and
Right.
the VT might reduce after a certain point.
Right, that's exactly correct. So you are just looking at the magnitude, right? You only want a measure of how big the changes are. You are not interested in the direction at this stage. So the direction,
One
yeah,
small thing. Sorry to interrupt. So I just was wondering, like, why couldn't have that modulus would have solved this problem? Like, instead of going to the square and increasing that value to that much, so modulus could
okay.
have
What do you think is an issue if you use modulus from a back propagation point of view?
module. Okay, that
It's not
differentiation
differentiable.
thing, differentiability.
Yeah, so differentiation is an issue. So this is much more smoother than the modulus.
Mm.
This is a smooth way of introducing the magnitudes.
Mm.
And your square root anyway kind of ensures that you are only scaling. So if you look at the textbook, what they say is this is effectively what it's throwing away the magnitude of gradient and only retaining its direction. So if you think about this, what is this effectively? What is this? This is eta by just look at forget the history part. Okay, forget that there is some history behind it, and set epsilon to be 0. So bt is just the square of the gradient, right? So if you take square root, what you end up with, you'll end up with the absolute value of uh, wt, right? Do you agree? If you take square root of a square number, you will end up with this. So this is eta into this. So eta into what is this? This is only this is what is the magnitude of this vector? In fact, not magnitude of the vector, but just look at every component in this vector. So what will be the value of every component in this case?
So 1 or -1.
Correct. Exactly. Right.
Like,
1 or
is it
minus
divided
1.
by the norm? Mm.
So it is only retaining the sign. So effectively, this is only telling you which direction to move. How much to move, that is decided by eta. Okay. Uh, so, but then this throws away the whole adaptive part, right? So you are not adapting really. The adaptive part comes because you are maintaining a history as opposed to just introducing the square of the gradients. So adaptive nature, if you want to bring in the adaptive nature, you need a history. Right? Otherwise, the adaptive part is gone out. But you kind of understand why the square root is added. So, if in the lectures you would have seen that if you remove the square root, it doesn't work well. That is again empirical. So, empirically, having the square root is what makes it work. But another way to understand it is if you add the square root, what you're effectively capturing is the direction of movement alone. Okay, and the history brings in the magnitude part or relative magnitude, how much to update.
But sir, if we didn't added the square root, then also we could have captured the same thing, but with a scale.
Yes, but again, so practice shows us that that doesn't work that well,
Mm. Mm.
right?
Mm.
So same, so we are not actually trying to escape uh, explanations, but certain things have not really been understood that well. Okay, so that's the main problem.
Okay, sir. And sir, before moving to the next one more small thing, what is the role of that VT plus that E part, the small
That is
that?
for numerical stability. So assume that there are some directions where your gradient is zero, the partial derivative is zero, then you'll have a zero denominator. You don't want to have a zero denominator. So that's for numerical stability. Okay.
Okay, so some kind of minimum threshold
Yeah,
kind of
some
thing.
10 power minus 8. If you look at PyTorch or some libraries, they'll have 10 power minus 7, 10 power minus 8,
Okay,
some value.
okay,
Okay, so the main issue with this ADA grad, so adaptive gradients, ADA grad, so is that the history of the gradient. So what is this? The history of the magnitude of the gradients. It keeps on growing. It's unbounded. Okay, it's monotonically increasing. And what the problem with that is that the denominator will soon grow really large, making the effective learning rate tend to zero. So if the effective learning rate tends to zero, then that particular, no matter what the gradient is, this part will become zero. So you will no longer learn. Okay, so learning will stall, and that is something we want to avoid. So we want learning to happen as long as we haven't converged to the minimum, and RMS prop comes in to prevent this unbounded growth. Okay, RMS prop very interestingly was not proposed as a research paper, so it was introduced by Hinton, right? I hope you all know who Hinton is. So Hinton introduces this in his Coursera lectures. Okay, so he did a series of lectures on Coursera, I think, and he introduced this in one of his lectures. If you go at RMS prop and look at the citation, it won't take you to a research paper. It will instead take you to this lecture PDF, lecture slides of his lectures. Okay, that is where this RMS prop lives. I found that very surprising. So all the others, I think there is a paper for ADA-grad, there is a paper for Adam, there is a proper research paper for ADA Delta, all these things. But RMS prop, you will never find a research paper. You will only find a lecture slide, mention in a lecture slide. Okay, so this RMS prop idea is very simple. You just introduce some kind of momentum to your, this is actually momentum term if you think about it. You introduce a momentum term to your gradient magnitudes. Beta, this is where the departure comes in the way you add momentum. So this is still exponentially weighted moving average, but then in this form. Okay, once you do that, this VT can now increase, decrease. It depends on where the window is currently situated. Okay, so remember this moving window analogy, right? So that's very useful here. So as your window keeps shifting, there might be windows where VT is big. There might be windows where VT is small. Okay, so that moving window allows for this kind of adaptive behavior, and that problem you get rid of in RMS prop. Okay, and then you come to Adam. So Adam is adaptive moments. Now it kind of combines the best of both worlds. So you no longer add momentum only to the gradients magnitudes, you add them to gradients themselves, right? So we know that momentum can speed things up, so why not incorporate that also, right? So this momentum here refers to the momentum added to the gradients, whereas the RMS prop, of course, is to your gradient magnitudes. Okay, so you do this, and then what you could have done is you could have directly gone here and done WT plus 1 equal to WT minus eta by all this into MT, but instead there is an intermediate step which is called bias correction. Okay, so this, now why is this bias correction required? It is one way, of course, there is a statistical way of showing this. You take expectation, and you would have seen the lectures, right? You could do that. Alternatively, think about this. You start with 0, 0. Okay. So from the point of view of moving averages, it's very unlikely for your gradient, your initial value to be 0. Correct? So what is momentum, and this what is it? What do MT and VT capture? They capture how some historical idea, right, of your gradient and gradient square. So when you initialize them to 0, you are actually sort of underestimating these values. Okay, you're underestimating both MT and VT when you set them to 0. So that is not such a good thing to do. So you bump these values by dividing them by 1 minus some fraction. Okay, that's an intuitive way of understanding this. I want to correct that. That is called bias correction. They are biased towards smaller values. I don't want that bias. I correct that bias by increasing their values. Okay. Now, what will happen when you are like 100 time steps into the algorithm? This will be negligibly small compared to one, right? So it will no longer impact empty hat. In fact, empty hat after 100 time steps will be nearly empty. Same is the case for VT hat, because once you reach those many time steps, your window has also moved, right? So you're no longer underestimating these values, you are estimating them correctly. So the impact of this bias correction will slowly disappear as you move to later and later time steps in your algorithm. Okay, so this is what you need to understand. You are underestimating in these values in the initial stages of the learning. Therefore, correct them by bumping their bumping up their values. Okay, this is one way of understanding the bias correction. Okay, so if you now look at Bishop's deep learning textbook, he says that sometimes they drop this correction in practice. So that is also something you have to remember. You should not think that this bias correction is sacrosanct and you have to include it. No, right? So sometimes in practice you also don't do this bias correction and it seems to work well. Okay, that is deep learning. Whatever works, you go with that. Okay, right? Now Adam, by the way, is probably the best optimizer in the DL world. So it's very good, so good that you can usually go with the default learning rate. So default learning rate is typically, I think, point not one or point not one, and you can actually train and it will train. It, the learning will happen smoothly, right? So Adam is quite good. Any questions so far? That
Hello.
yeah.
Yes, sir. There's a lecture in week 5. So there is actually I've also posted it on Discourse today. So there was it was related to the calculation of this these bias correction terms in
Okay.
the 6th lecture of week 5.
Lecture of week 5. Okay.
So basically, the professor is there trying to like it's a motivation for Adamax and a comparison of Adamax and Adam. So I'm not actually sir, quite sure about the calculations there. In V naught, the professor has done basically VT V0 divided by 1 minus beta 2 raised power 1, when it should be beta 2 raised power 0. So there, I'm a little confused over there.
Okay.
Sir, can I join from my PC and share the screen regarding the exact point?
Yeah.
Sure, just a moment, sir.
Okay. Any other questions so far? Yeah, so I'll encourage all of you to do the following, right? So please go back and look at Bishop, or there is another textbook which you can also look at, Understanding Deep Learning by Simon Prince. Okay, both of them are very well written. So go and read the chapters that talks about optimizers. It will be very helpful. Yeah. So you want to share? You need to.
Yes, sir. I'll just share screen.
Sir, can I share this completed PDF, sir?
Yes, yeah. Once it's completed, I'll share. Meanwhile, you can take a look at it here. So
Sure, sir.
you can take a look at. So I've written it down here. Same thing, whatever I discuss here, more detailed version I have it here, but I'll once this PDF is ready, I will share.
Sir, is my screen visible?
Yeah.
Sir, so here's the exact point. So basically here the professor is doing V naught, basically bias correction term. It is V0 divided by 1 minus beta. Beta has been taken 0.999. Beta 2 raised power 1. But in the formula it is beta 2 raised power t. Right, sir? So it should be beta 2 raised power 0. So this is where I'm confused.
Yeah, see, I also had an issue with the V-1 part. See, the V part, the confusion is with, in the case of Adam alone, this is Adam, right? Or Adam?
Yes, sir. Adam, sir.
Okay, so in the case of Adam, there is an issue. Okay, so You can stop sharing. I'll resume. I'll share this part.
Okay, sir. I've stopped sharing.
So with Adam, the issue is okay. So the same thing that we have been discussing so far, but how do you obtain or when do you obtain 1 minus beta power t? That's the question. Okay. So if you start with, if you look at all the other algorithms, for example, if you go back to momentum, the update is you start with u minus 1 equal to 0
Right, sir.
and then you continue the updates. Okay. So this is fine. In most of the other algorithms, you have a u minus 1 sitting somewhere. But in Adam, I actually tried. So if you try to have a v minus 1, or if you try to have a m minus 1, what happens is this has to be changed to beta 1 power t plus 1.
Okay, sir.
Okay, so I have actually done the derivation here. So if you do vt, so if you use this formula and if you actually expand it out, this works only if you have v0 equal to 0 and not v minus 1 equal to 0. So if you notice this part, right, where I'm hovering over,
Right, sir.
this becomes, if you introduce v minus 1 as 0, there will be a beta power t plus 1 term, right? So there your update has to be 1 by 1, it will be 1 minus beta power t plus 1.
Right.
So ideally, I would change the update equation to m0 equal to 0, v0 equal to 0, and then start this from m1, right? So
Okay, sir.
this, which means there is no concept of gradient of w0 here,
Right, right.
right? So only then will the, if the working is correct, this has to start from 0 and not minus 1. Which
Okay,
is
sir.
probably what you are referring to.
Right, sir.
You are having a 1 minus beta power 1 or 2.
Right, sir. It will be, yeah, that's the exact point of doubt, sir.
Yeah, so that's, but yeah, don't worry too much about this like small, the tiny issue. But in the exam, what we'll do is typically we'll give you, if you have to compute something with Adam, we'll typically give you the equations for Adam.
Okay, sir.
So that problem won't be there mostly.
Okay, sir. Thank you, sir.
Yeah, so we'll quickly go back to that part, right? The regularizers. So I haven't written down anything beyond bias variance. Okay, so the idea is
So,
very simple.
sorry to interrupt you there, but I got cut off a little. So, did you discuss NADAM as well?
No. Nadam. So I have restricted myself only to these optimizers, right? So Nadam, Max Prop, and Ada Delta even I have not discussed them from both from the course point of view as well as from a practical standpoint. These are essential. Okay, these are necessary but not sufficient. I won't call them sufficient, but this is a good foundation. I haven't discussed this in the exam. From the exam point of view also, we will largely be sticking to only these 7 optimizers.
Okay, so but do you plan to like cover maybe NADAM sometime? Because I had difficulty particularly in that because it combines NAG and ADAM and the look ahead term. It's quite complex, quite complicated, and there are just too many terms. I could not follow the lecture. So I mean,
Uh,
if you plan to do that, then it would be great.
we can study together if you want. I also didn't understand that very well. So I tried to understand it. I thought these will be covered in standard deep learning textbooks. But unfortunately, both, so I have looked at 2 textbooks, 2 of the most recent ones. Both of them stop at Adam. All of them stop. In fact, there is one more textbook. There are 3 textbooks that I am referring to. One is by Bishop, another one is by one prof called Simon Prince, third one is by one Charu Agarwal. Okay, all 3 are excellent textbooks, and all of them stop with Adam. So, and that's very few. So, if you really want to understand Adam and all the other things, we probably have to go back to the original research papers. Yeah, so I am currently not planning to do NADM because I myself
Okay.
don't understand it that well.
Okay.
Okay, so
There were some issues related to NADMs that were discussed on the discourse as well. I believe Siddharth is talking about the NETA term that is introduced over there. Anamika ma'am had said that that will be removed, but that still has not been removed.
okay, I will check with her. I will check. So there are some issues with some of the slides, I believe,
Right, sir?
where these corrections are pending. We have to do that. But yeah, so I faced a similar difficulty. I didn't understand. In fact, I kind of got lost after Adam. Until Adam, I could follow, but then I kind of felt that there were one two optimizers too many. And then when I looked at textbooks, they kind of confirmed my hunch that these are the core optimizers, and beyond that, we. So I just maybe I have the textbook with me. So before we go to this regularization, I'll just show you what typically they do. So I have Bishop here. So if you look at Bishop discusses so this is what are you able to see the sidebar, the contents?
Yes, it's visible.
Yeah, so there they discuss gradient descent, and then if you look at they do GD, they do batch gradient, stochastic gradient, and then they look at momentum, learning rates, adaptive learning rates, where they discuss mainly RMS prop and Adam. Okay, and that's all. Okay, so this is, by the way, this chapter is excellent, so you have to read this. So this is Bishop. If you look at Understanding Deep Learning by Simon Prince, so that fellow discusses again same equally good textbook. So they discuss. What do they discuss in gradients and no, this is backprop lecture. So fitting models. Okay, so they discuss. If you notice, gradient descent, SGD, momentum, and Adam. Okay, and then they discuss. They have a very small section on hyperparameters. That's all. So they all this fellow also stops with Adam. If you look at the final third, these are the three textbooks that I'm referring to. Third one is by Charu Agarwal. Okay, this is probably the best in terms of coverage. So this guy discusses more a wider set of algorithms. So he discusses momentum, Nesterov, ADA grad, RMS prop, ADA delta. He's slightly more comprehensive than the others. But that's all, right? So of course RMS prop Adam is there. So the only extra algorithm he discusses here is ADA delta. But fine, ADA delta anyway, it's kind of comes in the way. So that's all, okay? And then he doesn't discuss any other first order algorithms. He moves on to second order. Second order is out of syllabus for us. So where the Hessian comes in. So Hessian we don't discuss, right? So rest of it is, I would say, not a part of our syllabus. But even he doesn't discuss NADM and max prop and all that. Okay, so all this is not to say that you should not study these algorithms, but I wouldn't call them core deep learning algorithms, right? So you can, it is fine both from exam point of view as well as from a deep learning practice standpoint to focus on these core optimizers up to Adam. Okay. Yes. So yeah, see this entire week 7, right? Week 7 is all about week 6. Week 6 is all about this regularization. So how do you prevent overfitting? So this, you should be very familiar with this image from your MLT days, right? This is the most important image in all of machine learning practice, I would say. The loss curve versus model complexity. Okay, you will have a similar loss curve even if you look at loss on the y-axis and number of epochs on the x-axis. So typically your training loss will go down, your validation loss will go down up to a certain number of epochs, and then it will start increasing. Okay. And in practice, you have to keep monitoring this loss to get a sense of when to stop learning. Okay. Now, if you go all the way till the end, it means you are overfitting. You're going to fit the noise also. You're overfitting. So you'll end up with a high variance model, and naturally it'll have a low bias because it fits very perfectly, right? So there's a lot of capacity. On the other end, you have low variance and high bias, right? Meaning it's the model is too simple, right? Very simple models will have high bias because they can't even approximate the training data well. But then they'll have low variance because even if you give them different data sets and train different models on the same data set, the variance or the model that you will get will be relatively the same. Okay, so this does everyone understand what bias means, what variance means? Do you want me to go over this part?
So it's fine.
Bias
So
is
I
kind of
understand.
like loss, right?
Sorry.
Loss in other terms, we can call it as bias, right?
So okay, so maybe I'll quickly go over this. See, bias. So you have to understand the setup here. So okay, maybe I'll go over this, right? So there is, for you're looking at a single data point. Okay, so you have a single data point, and this is your true relationship. So the label or the output depends on the input, not deterministically, but with certain amount of randomness. Okay, this is called noise term, right? So it's some random error term or noise, and that doesn't depend on the input, right? So you could think of this as measurement error. For example, you're trying to measure the time, say y is time, y stands for time, and x stands for some vector, right, which is measuring, say, position. You're trying to find out the time taken for some quantity, and your measurement device is not going to be 100% accurate, right? There will be some imprecision, and that is captured in this parameter. Not parameter, is actually more of a random variable, right? So this is a random noise term. So what are you trying to model? You are trying to model f. You don't know f. So typically in the literature, if you see, f is a quantity that is dash but dash. So what do you think will be, will, if you want to fill in the blanks, how will you fill in the blanks? And maybe fill one of these. It's fixed. There is some fixed functional relationship, but that relationship is
Unknown?
unknown, right? So this is how it is characterized. So you know that there is some quantity which is fixed, right? But you don't know that, and therefore you have to model. So for example, this is very nicely captured in the laws of physics, right? So if you drop a ball from, say, 10 meters above, and it hits the ground, you know that there is some relationship between the time taken by the ball to reach the ground and uh, whatever quantity, right? So what does it depend on? It depends on, okay, rather the distance covered and the time taken, right? So u half gt square, those who remember your class 10, class 12, right? So the distance covered is a function of the time taken, right? So you know that there is some fixed quantity, but you don't know what it is, right? It's fixed but unknown, and you're trying to. So Newton's law, for instance, is only a model. It's actually not the truth. The true relationship, even to the state, you don't know. Newton's law is a very good model. So f hat in that case, it's a good model for the true f. So same thing happens in fact, something even more complex happens in our data science problems, right? So there is some dependence on of the labels on the features, which you know is fixed, okay, but you don't know what it is. This is an assumption, and you are trying to fit different models to it, right? So this in this course, it is a neural network. The model is called a neural network. In earlier courses in MLT, for instance, this model could have been anything from logistic regression to random forest to, say, AdaBoost, whatever, right? So what you need to take away is that this week 6, right, is actually an ML concept applied to a particular kind of a model called a deep neural network. That's all. KNN. So if you look at it that way, this week is nothing. There is actually nothing new in this week. So once you understand what a model is, you will be able to understand what bias is, right? So the main key here is this expectation. Okay, this I want you to understand. What is this expectation over taken over? So expectation is always when there is some randomness, right? So uh, what is the randomness here? What are you taking the expectation over? Do you get the question? So there should be some probability distribution, right? So some p of x. So e of x is p of x into x, right? So summation. So
Is
what?
it the model that is trained across various samples of the actual data set? So, like we take 30 or like out of 500 points in the entire data set, like we train the model multiple times on 100 randomly sampled points, and then we get a distribution for the models. Like, it changes everything. Is it, is it
Execution over the predicted value.
Exactly, right? So that is the randomness. So the randomness is over different data sets that you are. So the randomness is over is okay. So it's introduced by working with different data sets, right? So each f hat, okay, so each f hat is trained on a different b, okay, and that is where the randomness comes from. So if you look at e expectation of f hat, okay, x is fixed, right? We are actually trying to find out. We are Let's fix one data point, right? So the f hat, so the variability is in the f hat. So please understand that the variability here is not with respect to x. X, we are, if this is confusing, you can also call this x naught, y naught, so that you are talking about a very specific data point and not all possible data points, right? You are specifically looking at x, y naught, x naught, comma, y naught. Okay, that is for us given data point. So the variability, again, this is crucial to understand. Variability is in f hat. Okay, f hat is what changes. X naught also changes. You can, so if you look at it as a test data point, you can actually ask what is the overall expectation. But for now, when you look at E here, this E is because of different data sets that you are training on. Okay, so if you train on 10 data sets, you will get 10 f hats. So what will expected value of f hat of x be? If you train on 10 data sets, this will be summation 1 to 10. Okay, what will you be summing up? You will be summing up all those 10 different models that you had trained on 10 different data sets. This is the expectation. Expectation is what? Nothing but average, right? So this is the average value of 10 different models which were trained on 10 different data samples or 10 data sets. Okay, you are testing all of them on one data point called x naught. Okay, so this is the expected value. So that is what this expectation is. Bias is nothing but how far this is away from the true value f of x. F of x is the true value, right? Okay, so this is the actual relationship. How far is your model, right? How far is it from on an average, right? That's why the E comes on an average, right? If you take multiple data sets and learn multiple models, there will be something called an average model performance, right? So that is this. How is that compared to f of x, the actual model? So that is the bias. Statistically, if you remember stats 2, this is nothing but an estimator. This is an estimator. The bias is the difference between mean of the estimator and the population, the true mean. Okay, you can think about it as that way also. This is the square of the bias. This quantity is the bias. This is bias squared. Now, Variance, what is variance? How far you are away from the mean. Okay, so remember that variance has nothing to do with f. Okay, important point to note. So if you look at the variance formula, f of x doesn't appear anywhere. Of course, implicitly it appears in f in this point. Okay, sorry, no, not even implicitly. It appears nowhere. Do you get that? The variance has nothing to do with the true f. It has. You only bother about the different f hats that you are obtaining and how far away they are. Okay, so usually the way we understand it is, if you make a small change in your data set, by how much does the model change? That is what variance captures. So for example, you are you are testing at a single point x naught, right? So if you change d1, let's say d1 gives you f hat 1, d2 gives you f hat 2. So if you change small data point in d1, if that causes a big change in f hat of x naught, right? So if they are drastically different, if two models give drastically different value because of a small change in a data set, then that means that model is having high variance. Okay. Any questions in the bias and variance part? What these two concepts represent? Okay, then there is a trade-off, right? So this trade-off is what, where is the trade-off coming? You first of all you compute what is called the mean squared error. So can someone tell me what this is capturing? Or why are we interested in this quantity? This is the only thing that I know, right? I know the only thing I know is y. I don't have any idea about f of x, right? So I don't know what f of x. F of x is unknown. Whether it's fixed or not, I don't know f of x. Finally, I want to find a relationship between x and y, and my f hat is actually giving me y hat, right? So I am I am bothered about the y part, right? And how well my f hat is approximating that y. So this is the error. This is a squared error. So this is just the difference won't work. Therefore, you square it. And you are not just interested in the squared, you are interested in the mean squared error across different models. Okay, and this decomposes as bias plus variance plus the variance of epsilon. So this is what is usually called the irreducible error. So this is called the, because you can never set it to 0. I mean, so the mean squared error is MSE will be at least var of epsilon, right? You can't go below that. This doesn't depend on the model choice. This irreducible error is a part of the data set itself, right? If you think about it, this is how the data. So there is some loss term that will be introduced by this error. Okay, so I hope somewhat clear now. Okay, now yeah. So the main regularization technique is of course L2 regularization. You all know about that. It is, you don't want your weights to go too high, because that's a very good chance that it will start overfitting. So you add some penalty. The penalty is some lambda by 2. That is for convenience. We add this half into the norm of the weight squared. Okay, that is L2. L1 means you will take the L1 norm instead of L2. L2 is more convenient because once again it's easy to differentiate. Gives you a smooth loss function. Okay, so if you take the gradient, you do gradient descent, this is the update that you get. So what is interesting about this update? Is there anything interesting happening in this update? This is doing something to WT. What is it doing?
Reducing its value.
Yeah, so it is reducing its value. So this is often called weight decay, right? There's another way of understanding L2 regularization is to think of this process where you decay the weights. So decay means what? You steadily keep reducing the weights by a factor. It is 1 minus eta lambda. Okay, this is some fraction. Both are fractions. So this 1 minus eta lambda is a fraction. So you're going to decrease the weights. You can think of L2 regularization as a form of weight decay, right? So what are we saying? So L2 is a form of weight decay in the case of neural networks, right? Or even otherwise, you can think of it as weight decay, but let's say specifically here, that's what is happening. Okay, so you could have, for instance, I could have just called this eta lambda alpha, right, and call that the weight decay parameter, or 1 minus eta lambda is alpha, right? So if I call this alpha, then alpha is the decay parameter. Every time step, I am decaying my weights by alpha. Okay, so that's one way of understanding L2 regularization. Rest of it, I don't have anything specifically prepared. So this early stopping, you must know. Must have gone through it. So once you see that your validation loss is not decreasing, you kind of know that you have possibly reached the limit where you have to, where your model is going to begin overfitting, right? So your good days are over, so you have to stop at that point and output the model that you got there. So that is early stopping. Data augmentation is just adding more data points by subtly modifying them, right? So this is very useful in the case of image data. So you can rotate your image, you can scale your image, you can stretch your image by some amount, all that you can do, right? So that will increase the number of data points. And neural networks are very data hungry, right? So they want more data points you give them, the better it is. And data augmentation will also help you generalize better, right? Because, for example, in images, right? So a particular orientation might have not been there in the training data. So by rotating your images and doing other transformations, you are bringing in those possibilities also, right? So your model is going to generalize better. Parameter sharing and tying, we look at it once we do week 8. And noise at the input is also again very similar to some kind of augmentation. So if you look at the lectures, it argues that it is similar to L2 regularization in some sense, right? So well, that was a bit hard for me, so I'm not going into noise at the input, that derivation. Same for other derivations in this week. What you need to capture is the essence, right? So the derivations are good to know, but not mandatory if you ask me. So what you need to take away is the core ideas at a high level. Okay, so the most important of these is dropout, where you randomly choose certain number of hidden layer nodes and you drop them out, meaning you set them to 0, so that in that particular batch they don't participate in the forward prop or backward prop. Okay, so they are zeroed out, those units. And what this, so have you seen the lectures for this part? Why does dropout help? Does anyone know why dropout helps? What is the use of dropout? Any idea?
No, sir.
Okay, right. So there are some, again, these are all heuristic explanations. No one knows that this is exactly why it was. But so what it does is it makes sure that neurons not co-adapt, right? So this is a common phrase you will see in the context of dropout. So co-adaptation means a bunch of neurons ganging up together and trying to learn something. So, but not in a positive way, right? So, for example, 3 or 4 neurons in a hidden layer could come together and try to fit some noise pattern in the data set, right? So these co-adaptations may be bad and may cause your neural network to overfit. So you don't want neurons to a particular set of neurons to always fire in tandem, right? So you don't want to do that. You don't want that to happen. So dropout breaks neuron co-adaptation. Okay, so for obvious reason, right? So let's say neurons 1, 3, 5 co-adapt, and in one of the iterations you drop out one, you drop one out. So what will happen? 1, 3, and 5 can no longer co-adapt because one support is missing for 3 and 5. So they can't together uh, learn some noisy pattern. So that is avoided. So dropping out prevents neurons from co-adapting and learning patterns which are noisy. On the other hand, it also increases robustness, meaning neurons, particular class of neurons can't depend on each other. They'll have to learn to depend on other neurons also, right? So some redundancy is built into the network. So by building in some redundancy, right? Why is the redundancy? Because in every iteration, a different set of neurons are dropped out, right? So different parts of the network are required to learn the same kind of features. Okay, so if let's say identifying a face earlier without dropout, if say 3 or 4 neurons were responsible for identifying some feature of a face, because of dropout, different parts of that hidden layer are now pushed to identify that same feature, right? So that is redundancy. So you are not relying on only some hidden units to capture some feature. So, and when you increase redundancy, you naturally you increase the robustness, right? So it becomes. I hope you get that point. So redundancy boosts, makes the network slightly stronger, and you can also view dropout as an ensemble. That's also some kind of an ensemble, right? So at least during training, this is what is happening, right? So in each iteration, each batch, you are training a different neural network. Okay, so therefore you can think of not training just one neural network, but training a huge collection of neural networks. So it can be thought of as some kind of an ensemble. All right, so that's all there is for week 6. Essence of week 6 is these things, right? So main methods I would say are dropout uh, and L2 and trying to understand the bias variance trade-off. Early stopping is very intuitive. Data augmentation is also intuitive. Rest of it is yet. So one thing I missed out is noise at the output. So that is also important. So noise at the output, what you do is input you add some noise. That is one. Noise at the output is if you take up a classification task, right? So instead of having hard target, so what is a hard target? If you're having 4 class classification problem, so your label vector will be a one hot vector like this, right? This is a hard target where one of these values is exactly 1, rest are all 0. So you kind of make it soft by adding some noise. So soft targets will look like this. So what you do is you take away some of the weight from the true label. You take some epsilon of it away from here, and then redistribute it. So this becomes epsilon by, what does this become?
Epsilon by 3.
Epsilon by 3. Epsilon by 3. Okay, you're redistributing your very small. Okay, so this should not be like 0.5. Okay, then there's nothing. You can't learn anything. So this should be like say 0.001, something as small as 0.001. So this becomes a soft target. So this is this is noisy, right? So it's not exactly one. So you're introducing some noise into the output. Okay, this similar thing will happen at the input for the case of the noise at the input. So some small epsilon you will add. So in the case of images, you is usually called, so you usually add white noise, right? So you add a Gaussian noise. So to each pixel, you add some small value which is drawn from a zero mean Gaussian distribution, right? So that happens. Okay, so that is effectively what we have for this week. Okay, any questions? Okay. Okay then. So week 8 is probably like the most important of all 4 weeks for quiz 2. So please spend maximum time on week 8. Okay.